Welcome to this explainer. Have you ever wondered how some engineers can look at a terrifyingly complex circuit and just solve it in their heads? Like in seconds? Well, today we're going to take a deep breath and transform those intimidating, tangled circuit diagrams into something calm, predictable, and honestly, remarkably simple. If you're a college student deep in the engineering trenches right now, you know exactly the kind of chaos I'm talking about. So let's clear it up completely.
Ever looked at a circuit and felt completely overwhelmed? Because if you've ever stared at a dense textbook page filled with messy nodes and loops and just felt your stress level spike, you are absolutely not alone. It's kind of a universal rite of passage to look at an electrical engineering homework problem and think, where do I even begin?
Let's look at a complex circuit like this one for a second. You've got multiple interconnected loops, resistors branching out everywhere, and a mountain of dense algebraic equations just waiting to be solved. It feels like a massive tangled knot, and honestly, it is completely natural to feel a bit of panic when you're trying to track voltages and currents going in like a dozen different directions at once.
So, let's talk about the core idea here: simplification. Think of this conceptually as a magic eraser for all that visual noise. It's a lot like plugging your phone charger into the wall. You don't need to understand the entire city's power grid to charge your phone, right? You just need to know what happens right there at those two outlet prongs. We're doing the exact same thing here. We're treating massive networks as a simple black box and focusing strictly on the two terminals where we actually plug things in.
And that brings us directly to Norton's theorem. By definition, this theorem is just a beautiful, elegant tool that lets us replace an entire terrifying web of linear components with just two simple things: one single current source, which we call I short circuit, and one single resistor, known as Norton Resistance, or RN. That massive schematic from earlier, it literally condenses down into just these two basic elements sitting perfectly parallel to each other. How cool is that?
Okay, so how do we actually get there? Let's look at the procedure, our safe roadmap.
To reach that beautifully simple endpoint, we really only have to focus on three manageable steps, just taking them one at a time so we don't get overwhelmed. Step 1, we short the branch we're investigating. Step 2, we find the short circuit current. And step 3, we calculate the equivalent resistance. That's the whole shebang. If you can handle basic circuit analysis, you can easily follow this map. Let's zoom in on step 1 and find that short circuit current.
To find our Norton current, we just draw a short line, a literal flat wire, right between terminals A and B. Imagine you're bypassing a terrible traffic jam with a direct, zero-resistance express highway. By doing this, we get to temporarily ignore the rest of the network's noise. Our only goal in this exact moment is to find the current flowing through that specific isolated express path. And boom, that gives us our Norton current.
Moving right along, let's talk about finding the equivalent resistance. Next up, we deactivate our active sources. What this means is we take our voltage sources, say a 10-volt battery, and replace them with a simple flat wire, effectively short-circuiting them down to 0 volts. From there, we just calculate the total resistance looking back into our two terminals. It basically turns into a straightforward, low-stress exercise in combining parallel and series resistors.
Now for the really fun part, putting it all together. This is where we get to experience the deeply satisfying payoff of our methodical approach. We take our isolated findings and assemble them into one clean picture, placing our calculated single current source neatly parallel to our single calculated resistance. We have completely tamed the initial chaos into this elegant, highly manageable circuit. And the best part? Any load you attach to these terminals is going to behave exactly the same way it would have in that massive, terrifying original network.
Before we finish up, I want to introduce you to Thevenin's helpful twin.
You see, Norton has a twin sibling named Thevenin, and they are literally two sides of the same coin. While Norton uses a current source in parallel, Thevenin uses a voltage source in series with a resistor. And thanks to a simple source transformation using Ohm's law, knowing one means you instantly know the other, so you're never really starting from scratch.
I want to leave you with this practical, low-pressure takeaway. In engineering, and honestly in life, when you're faced with an overwhelming, chaotic problem, don't try to solve the whole thing at once. Take a breath, isolate the pieces, simplify first, and let the clarity follow. But it does beg the question, if Norton and Thevenin can turn massive, chaotic circuits into two perfectly simple components, what other overwhelmingly complex systems in our world are just waiting for the right magic eraser to make them perfectly simple? Thanks for hanging out with me for this explainer. Catch you next time.